Hey, how's it going? My name is Sandy Walsh. I'm a software developer with a company called Planet Labs out of San Francisco. I live here in Halihax. Thanks for coming out. I know there's a lot of places you could have been tonight. Came here, great. So I'm going to talk a little bit about flight software, which is a software that runs on satellites or spacecraft or whatever. And there's a bunch of assumptions I'm going to make here, so I have some questions. Anyone doing embedded software or like anything like aerospace or? Okay, great. Except for Mike, I can lie all I want. So these are actually a couple of our Dove satellites getting kicked out of the International Space Station in the early days of trialing this stuff. Basically, the premise came from a couple of our founders. We're like, well, why does it cost so much to put a satellite in space when basically that has everything you need on it? It's got cameras, it runs Linux, it's got accelerometers on it, GPS, so why can't we just do that? So that's basically some of the first ones that came out when the Russian astronauts were yelling out mini Sputnik and then tossing them out. So now I'm not going to talk about rockets. Basically, the assumption here is that your satellite has made it into space safely. Space is hard. This is the Antares rocket, which went up, I think, in 2016, 2015. We had some satellites on this, and space is hard. So, but we've been on a variety. We'll ride on any rockets at all that go up. A lot of SpaceX. There's a bunch in India that we use. Yeah, so. Actually, they found one of the satellites on the beach, and apparently it powered up, so I don't know. So I'll just show you what we kind of do is we have, this is a Pelican satellite, which is our new one. We just put up a test demo back in October, I think, of the first one, TD1. And so it goes in a sun-synchronous orbit around the Earth, and it's got a big camera on it, and we take pictures of the Earth every day with it. Now, one isn't going to do it. You're not going to get a picture of the whole Earth every day, so we send up a whole fleet of these, and then over time we send up more and more fleets of these, and we might even go in different paths around the Earth so that we can get more coverage. But basically the idea is that you can get a picture. We have a smaller one as well called a Dove. I'll show you that in a second. But basically you can get an entire picture of the entire Earth every day with these satellites. So these are our Doves. These are the ones that you just saw getting kicked out of the space station. We practice a thing called agile aerospace, where we basically iterate on these things all the time, right? There's all different flocks that we put out. If something doesn't work, we tweak it. We're changing the software all the time. So these are the iterations of the Doves that you see. Now we have the Super Doves. These are technically called cubesats. So I think Mike will get into a little bit more detail on this, but a cube for aerospace is 10 centimeters by 10 centimeters by 10 centimeters. These are a 3U CubeSat, so 30 by 10 by 10. Most of it is basically a big camera. It's just basically just a big lens. And in the back of it, there's a little computer that does all the stuff. So really what I'm going to be focusing on is the satellite, but also specifically about the software that runs on that little computer. This is Pelican. This is the new one that we just put up. It's a lot bigger. It's probably about the size of this table, I'd say. And then with the solar panels out, it probably comes out about here. So that one just has a much bigger camera, but basically the architectures are very similar. But I'll get into some of the differences. So how many people here are developing cloud applications? Right. So probably on one of these clouds. Right. If you're doing that, you've probably got some sort of an architecture like this. You've got some sort of a client, maybe it's a web client. You go through some load balancers, use some authentication. You're talking to some microservices. Maybe you've got some queues. You've got a database where you're storing your data and sending your data around. Right? Does it look familiar? Very similar to what we do. There's reasons you do that. Like there's a reason that that's a common architecture. Right? Because you have different use cases where you have synchronous and asynchronous communication that you need. You have to deal with storage. You want microservices because you want a separation of concerns between all your functionality. And then you have to deal with security. You might scale that up. You've probably got Kubernetes or some other autoscalers in there for growing this thing out. You probably do some sharding of your database. Oops. Then you've probably got different regions that you run in your cloud. You probably run in a US and probably a European data center where you can get some more redundancy. So that's really what, when you're building web software, or cloud software, that's really what you're concerned with, right? How do you deal with capacity? How do you deal with redundancy? We have to think about redundancy as well. Redundancy is a big issue, but capacity is kind of fixed for us because it's a satellite. You can only take so many pictures at a given time. So our architecture is very similar, but it's a little bit different, right? So our client is basically a bunch of binary protocols. Then we talk to a ground station, which has some radios in it. And those radios talk to radios in the satellite. Then there's some security stuff that we do. I can't get into a lot of variable details about what we do, but a lot of hand-wavy stuff here. So then we have the flight computer, and it runs a bunch of Linux services, and we have different services for different things. There's queues that we use to talk to between the services. There's devices that are boards that are attached to the flight computer that do very special things for us. And I'll get into some of that. And then those boards might have their own storage, and then actually the flight computer has its own storage, just like any Linux box would have its own storage. We scale that up, right? So that's a package, that's our satellite, and then we ship that off into space. And then as we scale that up, we have multiple satellites, and then we have multiple ground stations spread out all over the world. And then basically that cloud software that you're used to building, that's what we have on the ground. So we've got this huge auto-scaling cloud infrastructure that deals with, well, where is the satellite? Where should it be pointing? What are we taking a picture of? What do we want to do? So that's, we're talking tens of thousands of containers and virtual machines and everything just on this side of the line alone, let alone what's up in the satellites. So it gets kind of big very quick because when you're dealing, so we've got a couple of hundred of these little Dove satellites up there now, and we just got the one Pelican. Before that, for large satellites, we had Google satellites, which are the cubesats, and I think it probably still got probably six or so of them up there, which are the high-res ones. But we're switching over to Pelican, and you can't manage those manually. You can't have a person sitting in a chair trying to control these things manually, right? So everything has to be automated. Very similar architectures. If you look at a modern car, you're looking at a lot of the same sort of stuff. Just so the design criteria is a little bit different. So this is what in the industry now, they call this a software-defined vehicle, which I think is pretty funny. But a lot of the same design considerations in automotive that you would see in a satellite. Your cell phone, very similar as well, right? Just different design considerations. Over-the-air updates, how do you get software to it? How do you get data back from it? All that sort of thing. So this gets us into this world of embedded software development, and it's no different than knowing a cloud stack. It's just some protocols are different, and the tool stack that you use is a little bit different. You're probably not writing in Golang because that's not going to work on a embedded device, but you still have to do all the same CI and test and gating and builds and version control and all the rest of it that you do today. So like I say, our design criteria is a little bit different. We are focused on redundancy and power management, not capacity, because capacity we get by having more satellites. So if you look at a cell phone, redundancy is basically none, right? That's it, you use it, if you break it, you get another one. Cars, they might have a little redundancy in there, maybe on the braking system, on the airbags, that sort of thing. Airplanes, more redundancy as you move up the stack. Satellites, very high in redundancy. Bigger spacecraft, very high in redundancy. It's like a boat almost. A boat has tons of redundancy as well. Power management, hugely important for us. As you move down the stack, they're less concerned about power management. Phone is actually kind of concerned about power management. But cars, and unless it's a fully electric vehicle, cars and airplanes have their own means of power generation on board, so they don't really worry about it so much. We have it as well with solar panels, but that can be a little hit or miss. The other thing is, why have all this redundancy? Well, you can't bring it in for a service call, right? You're not going to go into space and fix one of these little satellites. You had to assume that it's fire and forget. So there's an interesting phenomena that can happen in space where a 0 can just turn into a 1 on your computer. So that's something that we have to test for. We hit it with particle accelerators and see if we can simulate, what's called a single event upset, and see how the software deals with it. Then there's vibration testing, the heat testing, and all sorts of other fun stuff. So as we look at the flight computers, at the satellite, if we break it out a little bit, we've got the flight computer, and then in terms of redundancy, we've got multiple kernel images that are there, multiple root FSs, we've got our user data and everything, and then all these outboards that work for the radios, for taking power from the solar panels, charging the batteries, consuming power from the batteries, security stuff, how do you switch power on and off? You don't want to give the same power to everything all the time. You want to be able to control that sort of stuff. So that's where we do a lot of the dance. And at any given time, any one of these sets could be on. So we might turn off flight computer A for a little while. We'll boot from kernel 1 or kernel 0, and then we'll probably bring down the MPPTs for a little bit and do a partial charge, or there's quite a dance that goes on there. Let's talk about protocols for a second. In the conventional cloud architecture, you've probably using stuff like this, right? You've got HTTPS. You've got, if you're doing queues, you're probably using AFQP over TCP. If you're talking to a database, you're probably using some binary protocol, Postgres or MySQL or something, which is just a binary protocol over TCP or UDP. In between your microservices, you're probably using gRPC or HTTPS. Pretty standard stuff. In the embedded software world, talking to the devices gets a little bit more tricky. So you'll have different protocols like your standard sort of UART, which is serial communication, just very bare bones. There's other ones called I2C, SPI. You might just be doing UDP communications. So there's just different protocols that you have to be aware of as you're talking to all these sensors and stuff as it moves down. And the design decisions that you have to get into, like, why do I use I2C? Why do I use CAN flexible data? Why do I use a UART? It really depends on how far is the wire that you've got to send the communication over. It's going to be a noisy environment. Just a bunch of little design decisions that you have to make there. The CAN flexible data is an interesting one because it's not one that you hear about a lot. If you've played around with an Arduino or anything, you've probably done I2C, you've probably done SPI or something like that. CAN is an interesting one. It was developed for the automotive industry, Bosch in '83 actually, and it's basically just two wires with terminators on the end, and then you can plug in anything into it, any nodes into it, but they don't have any addresses. They work on priority of the messages. So it's kind of a neat system. So, and that's the way all your cars operate this way. You plug in these different systems. It could be your airbags or your anti-lock brakes or whatever. And they plug in and they start, there's one node which will start off a communication and it'll say, okay, I want to talk right now. And it'll start with a starter frame message up here on top. And it just starts sending out information on the line. And as soon as it starts transmitting, it changes signal on the line. All the other nodes will start transmitting as well. And they all listen at the same time because the way that the bus is designed, they can transmit and they can listen. And what they'll do is, if they try and transmit a 0 and they see someone else has written a 1 on it, they'll go, oh, I don't have control of this. Someone has higher priority. And then they back off. So eventually, all the nodes will drop off as it gets, because everyone's sending the same data until all the nodes start to drop off. And then there's only one person left. And that's how the message gets out. So it's a neat little system. CAN flexible data versus CAN, basic CAN bus. It's just slightly different packaging on it, but it's neat. The Cybertruck is an interesting one, just came out recently. We've seen all the news and stuff on it, but they made a decision not to go with CAN bus. They did IP right across everything, right? And they did 48-volt power over Ethernet across the whole truck, which is kind of cool. Anyway, it's a little bit of a rabbit hole, but I think it's fun stuff to think about if you're building something. All right, let's get back to satellites. So let's look at the stages of a satellite when it wakes up. I jump around a little bit on this presentation, so bear with me. So the very first thing is that the satellite is on the rocket and is waiting to get launched. And it knows that it's on the satellite because there's this thing called a GPDP, which is a ground power and data port, which is basically just a switch on it. And it says, you're on the rocket. And it goes, cool, I won't do anything crazy. And then it gets kicked out and it goes, oh, that switch is not there anymore. I guess I'm in space. And that's really as simple as it is. And then when it comes out, it's tumbling, it's rotating, it basically has no control. And then the only thing it's trying to do is it's trying to get a signal from the ground. So it's looking with a very broad antenna to try and get some sort of signal from the ground. The yo. We used to have a Twitter account that said yo. We didn't tweet it out yo every time one of our satellites picked up the first contact. So then it does a little dance, and I'll get into the dance in a little bit, where basically the solar panels will open up and the antenna will come up and it'll stabilize itself. So then once it's stabilized, then it can control itself. These are so small, there's no thrusters on these. So basically whatever the rocket threw it out at, that's what it's doing. It's traveling in that same path. But it can rotate around in its axis. So it'll aim down, take some pictures, look for a North Star, look at the moon, find out where it is, find out where a ground station is, send some data back down to it, and then it'll also at the same time get updates on the software. So it's like, hey, you got some new software, you got some new stuff, give you all the data, and that's the whole rinse and repeat lifespan of a satellite, basically, because you're not going to update the hardware or anything that falls up there. So I'll dig into some of that now in a second. There's a big team that's behind all this. So I work on the flight software team. We have people that take care of the orbits, the ground station operations, payload, optics, thermal controls, electrical engineering, mechanical engineering, you name it. There's an entire mop of people. And that, like I say, this is just on this side of the line. This is basically from the ground station up. There's an entire other half of the company that takes care of the stuff when it hits the ground station in the pipeline. So let's look at this one scenario here. Satellite comes out, it's tumbling around, needs to get stable. How do we do that? So there's a system called guidance, navigation, and control. It's an old Apollo photo, but basically it's for controlling the satellite. And then there's a bunch of tools that it can use to maneuver. Like I say, there's no thrusters on it. I mean, the Pelicans do have an ion propulsion system on it, but for the Doves, which are a lot smaller, they use systems called magnetorquers, which are just big electric magnets. There's enough of the Earth's electromagnetic field that you can fire these things up and flip them around off the magnetic field of the Earth. So those are great for big moves. And if you want to get really fine with it, then you use these things called reaction wheels, which are basically like dentist drill motors. So whichever way the motor turns, there's an equal opposite reaction, and it can adjust that way. You can only go so far with a reaction wheel, right? After a while, it'll just max out, just like your phone. You don't see it vibrating off the table all the time because it can only move so much. That's basically a reaction wheel, those little motors that are in that. So that's when the magnetorquers kick in and do the big movements. And then, like I say, there's cameras for looking at the stars, GPS, inertial movement units, all kinds of different sensors. So from flight software, there's this entire bunch of math, I'll just keep it simple like that, where we farm sensor data into it, and they send out a bunch of commands to us on what to do. Fire up the magnetorquers, get us into this orientation. And and we just give them an API on how to get data in and how to get data out. And then so the GNC team can do whatever they want, come up with all different schemes and strategies for how they're going to do all this sort of stuff. We don't have to worry about it. We know that here's how data gets in, here's how data gets out. There's one cool little thing they do when the satellite first comes out and it's tumbling. And let's say it's tumbling this way, and we want it to go back that way so it can stabilize. It'll do what's called a toe dip. which is just a little, test the water type thing. So they'll try and like move a reaction wheel to come back. And it's just to make sure that you've got your plus signs in the right place, your plus and minuses in the right place, because that's a common mistake. You think like the math works perfect, but it was just the signs were wrong. So you do a little toe dip and just see if it works. Did it speed up or did it slow down? And then after a while, you do another update. Just keep going like that. So like I mentioned, when the satellites come out, they're all in a bunch, right? So the rocket's flying, spits out all these satellites, and they're basically in a cluster. That's no good to us. We need to have them spread out around the Earth. There's no thrusters, so what do we do? Well, we're in low Earth orbit, which is basically below 690 kilometers. We're actually flying around 400 kilometers, plus or minus a bit. So there's a bit of atmosphere there. And what they can do is we can tilt with the wings out. Sorry. We can actually ride that little bit of atmosphere with the solar panels and have it spread out that way, just like riding a wave, which is crazy. There's a lot of factors you have to take into account there: lift, drag, thrust, gravity, solar radiation. This one I thought was pretty cool. Is Lorentz force. So basically, the satellite becomes a charged particle going through a magnetic field, and then that changes all the measurements and stuff that you have to account for. It's not a big number, but it is like just a crazy factor that we run into. So the other thing we have to worry about is the radios. We have a bunch of different radios. Some are very broad and wide swath, and then some of them are very targeted but high speed. So we'll start off with a wide swath, and then we'll find our ground station, get a lock on it, bring it in a little tighter, higher speed, bring it in super tight, start uploading and downloading software and images and all the rest of the stuff. Finally, we have payload. This is Carbon Mapper. JPL is building that for us, which is going to be in our Tanager satellite, which is going to be what they call Carbon Mapper. So it'll be able to find out who's emitting the most carbon around the planet, which is crazy cool. But we just can bolt that on and keep all the same basically structure of the satellite, the main body of the box and everything. So that gets us down to flight software. So what does flight software actually do? Well, like I mentioned, there's a bunch of APIs for talking to all these systems, right? So we have our Linux box, we have all these boards, we have all these sensors, and then we have APIs that talk to payload, to GNC, to the radios, and we exchange data back and forth between them. Yeah, you can see that on the Pelican over there. The white part of the Pelican is the payload, right? So we can swap that out and put in Carbon Mapper, for example, or some other payload. So we're concerned about RPC, remote procedure calls, right? How do we do RPC to all the different services and stuff? Now, there's a bunch of off-the-shelf stuff that you can do, but there's certain design considerations that you want to have with it. In terms of, do you want to do TCP, do you want to do protobuf? I mean, there's all kinds of different tools for doing that. So we have to set up an RPC for talking to all these pieces. We're very focused on time. We're in space. So yeah, you can do Greenwich Mean Time, you can do UTC, but if you don't have a satellite lock, how do you get that? How do you know what the time is for updates, and is this the right version of the software and all the rest of that stuff? So that's another one. And also, we had to get the time out to all the peripheral boards as well, because they sort of run on their own. So we need to tell them what time it is. So someone has to be the keeper of time on the system. This is where it gets a lot like back-end software, right? We're worried about telemetry. If you've got a dashboard where you do telemetry on your cloud software, we do a very similar thing. So all these boards and everything spitting out telemetry, but they don't go to the ground. They just go to the flight computer, and we just track it. We just keep it around there. So if GNC needs to find out about, how are the batteries doing, or what's our orientation or anything, we have all that data around that we can pass out to all these different systems. Events, so like telemetry, which is an instantaneous measurement of something, an event could happen, which is like we started a sequence, we ended a sequence, we put the battery, we put the solar panels out, we started doing a rotation, whatever, one time, start end type events. We have a system for doing that. Scheduling, at a certain time, do a software update, at a certain time, take some photographs. Managing all that side of it is equally important. Orchestration, after you've done this, do this. If this happens, don't do that. All the branching logic. So you don't want to hard code that. You want to have a system which is flexible, and we can upload it from the ground station. Say, here's your new sequence. Faults. If you've got a dashboard, you know how you've got to be able to do traffic lighting on all that stuff. Green, yellow, red. Everything's good. Well, that all happens on the satellite. So all the orchestration and alerting dashboards and stuff that you would normally see on the ground, there's an entire system for it on the satellite as well. So what we would call alerting in cloud software, they could just call faults. So has a fault occurred? And then finally, getting software updates and updating a running system, and then getting data backed out. So imagery, payload data, or carbon mapper data, which is not images. It's carbon sensor data. So like I say, it's basically back-end cloud software at space in a nutshell. If you're interested, if you want to learn about real-time operating systems, which are sort of core to all this sort of stuff, that's a great way to get started. If you want to learn about building your own embedded Linux stuff, there's a couple of tools called Yocto and Buildroot, which are cool for doing that. And there's an open source radio that we open sourced a few years back, probably 10 years ago actually. So if you are building a satellite, there's a way that you can have a radio sort of out of the box to use. And NASA also has open mission control software. So all that stuff on the ground for controlling stuff, a lot of this you can get. There's NASA, JPL, and everything have been open sourcing a lot of their stuff for years. So file transfer stuff and all kinds of different tools are out there that you can pick from. I don't know where I am on time. So that's about it.